Alright, this is my Nash equilibrium calculator. It's used in game theory. The Nash equilibrium, real quick, I'm going to go over to my week 11, the discussion board post for my project, my research project. I've been learning a lot more about game theory and kind of how it works. And so if you look here, it says, in the Nash equilibrium, each player's strategy is optimal when considering the decisions of other players. Every player wins because everyone gets the outcome they desire. So I wanted to take that and build a little model in Excel on how this could work and how you could use these things called payoff tables to calculate what the Nash equilibrium is. So up here, these are my input tables. So I just modeled rock, paper, scissors using game theory. So if you look here, this is the payoff to A based on the decision by player B. And so in this rock, paper, scissors model, if player B chooses rock and I choose rock, then my payoff is 0 as player A. And then if player B plays rock and I play paper, well, I beat rock, so I get a payoff of 1. But if player B plays rock and I play scissors, then I get a payoff of -1. So that's kind of how I modeled this. So, and then this is kind of the opposite. This is the payoff to player B based on the decision by player A. So over here, you can see this is the maximum of the columns, or the rows, sorry, and this is the maximum of the columns. So this is using ones, -1s, and zeros, but there are other ways to calculate payoffs. Rock, paper, scissors is pretty simple. You either win or you lose. There's no real, like, oh, well, if he does this, I could get a payoff of 2, but if he does this, I could get a payoff of 5, etc. There's just a lot more complicated that can be done. I chose to go the simple route and just kind of show how this would work. So you can see this table down here is basically just ones and zeros showing where the maximum value is. So you can see up here this correlates with that. Down here that correlates with that. And this one and that one. Same over here, but with the other table. So Nash equilibrium would occur where both of these values are 1. So if you look at this formula up at the top here, it says if and F22 equals 1 and K22 equals 1. So what I'm saying is, if both of these are maximized, what that's telling me is, okay, well, I can get the maximum return from what I want, or my maximum payoff, no matter what, because, whoops, we'll undo that. So if this was my max and this was my max over here, that's a Nash equilibrium because we are both getting the maximum payoff possible. That's a Nash equilibrium. So just for example, just to kind of show how this works down there, what if in the game there's a new rule that says if we both choose scissors, we get a payoff of 2. So I put those in. Boom. This is how the Nash equilibrium works. So this is a really obvious example. If we both get a payoff of 2 here, well, of course that's gonna be a Nash equilibrium, right? Like I said, this model is really simple, but there is other applications as you get more complicated. So again, what if this one was 5 and this one, oh yeah, this is already the maximum there. So that's a Nash equilibrium. Even though this is 1 and this is 5 for player A, this is still a Nash equilibrium because it's the max payoff for both based on the other person's decision. So that is kind of how Nash equilibrium works. That's how the model works. It's pretty simple. It was really fun to build, and it was fun to learn about the Nash equilibrium and the other types of game theory. There's cooperative and non-cooperative, and there's lots of other ways you could take the game theory. And I just really enjoyed learning all about that and how there's a lot of science and math that goes behind decision making. So thank you guys. I hope you enjoyed this, and let me know, if comment on this discussion board if you have any other questions or you're impressed or whatever by this. I had a really fun time making it, and I hope you guys have a great day. Thanks.